Good morning, and my name is Dr. Chimba from Tennessee State University. So we started this project last year, and basically we are trying to evaluate the impact of using transit priority signals to see how we can improve the travel time for the transit. So the study responds to the problem facing Tennessee, especially in Nashville area, where we have a very, very bad traffic condition, and that affects the movement and growth of the city. So we expect that the study findings will be used for transit-oriented development. So what we did actually was transit signal priority. And we have a lot of benefit from using this type of technology or type of process. So the literature says that if we use TSP, it can boost transit movement, it can reduce bus bunching, it can improve transit or bus scheduling, it can reduce auto dependency, it can expand mobility, it can improve transit leadership, and so forth and so forth. So why did we choose Nashville? Nashville is growing very fast. According to the recent statistics, we find that about 94 people move to Nashville every single day. That is approximately 35,000 people in a year. And there's high traffic congestion, poor bus serviceability, and also only 1.5 to 2.5 residents of Nashville use transit or buses. According to Wash, you can see there our Washington Journal. I don't know if you can see it there well. They say that Nashville is growing, but there's a problem of how to move people around. So the objective of this research was to evaluate the bus schedule adherence in terms of the bus recovery at bus stop level, to determine the bus travel time reductions, to find how the operation of transit signal priority can affect the major and minor street delays, and also the overall intersection level service. So based on that, the approach which we used was to use a simulation. We use a VC micro simulation, and we pick a corridor, very, very long corridor in Nashville area to start with. I mean that later on we are going to add more corridors. So how about this corridor? Is called Gallatin Pike. Is about 12.3 miles long. It has 2 lanes each direction, and then we have a 2-way left-hand lane in the middle. And then it has about 48 signalized intersections and around 104 bus stops. So that is the corridor which we picked. So in this particular presentation, we are not going to present the result for the whole corridor. We just pick like 1.83 mile long to start with. And this one, again, is a 4 lanes with the 5th lane is a 2-lane continuous lane in the middle. It has 9 signalized intersections and 7 bus stops. So my student will pick it from here, what we did, and give you a little bit how we model it in the VSIM and the preliminary result which we are getting so far.
Thank you very much, Dr. Chamber. My name is Sotonye Ikiriko, and a graduate research assistant at Tennessee State University. Okay, just like my just like my professor earlier stated, transit signal priority is simply giving preferential treatment to transit vehicles at signalized intersections in order to speed up transit vehicle movement. Okay, for example, if a bus is approaching an intersection and the signal is red, the red time is truncated and the green time is returned so that the bus can go through the intersection. So how does TSP operate? TSP has 3 major components: the transit vehicle detection system, the communication system, and the traffic signal control system. The traffic vehicle detection system creates a vehicle to infrastructure communication between the emitter from the transit vehicle and the optical detector, as we can see from the picture on the slide. Okay, so when there's a communication between the emitter and the optical detector, this communication generates a priority request, which is sent to the traffic signal control system via the communication system. So basically, this is how transit signal priority. This is the principle behind transit signal priority. So to achieve our methodology, as earlier stated, we followed strict guidelines for applying microsimulation software to transportation research. These guidelines were actually set by the Federal Highway Administration, so we followed these guidelines strictly. The first thing we did was to select our microsimulation tool, and we chose the Vism microsimulation software. We actually chose Vism microsimulation software because Vism has the ability to model almost any traffic control logic via what is called the vehicle actuated programming language. So this is actually why we chose the Vism micro simulation software. So after we chose our simulation software, we carried out data collection, which I'll explain in subsequent slides. So part of the data we collected is turning movement counts. That's traffic volumes at each intersection along our corridor. Okay, so we use these traffic volumes to generate an origin destination matrix based on the principle of conservation of vehicles, which states that the vehicles in a network can neither be created nor destroyed. This means that the number of vehicles entering into a link or a network must be equal to the number of vehicles leaving that network. So this is the guiding principle behind our estimation of our origin destination matrix. So after we estimated the origin destination matrix using our turning movement counts we got from the field, we validated this origin destination matrix to make sure that our estimation closely matches what is on the field. We are going to see the result of the validation. So after we validated our origin destination matrix, we went further to develop our model in Vism. Our model development process will be explained in subsequent slides. Okay, so after we developed our model in Vism, we went further to calibrate this model, because if any model that does not represent or replicate the real situation cannot give accurate results. So this was actually why we calibrated our Vism model, and we went further to validate the model. This will be explained in subsequent slides. So after we were sure that our model replicates field conditions, we added transit signal priority to the model to measure delay, bus travel times, and delays on side streets. So we developed a code using the vehicle actuated programming language, and we coded green extension and red truncation priority strategies, which will be explained in subsequent slides. So for our data collection, we extracted roadway geometry data from Google Earth, and we extracted intersection layout, the lane configuration, bus stop location, and type. So all these were extracted from Google Earth to be coded in Vism. And then we collected turning movement counts, like I earlier stated. We used what is called the Mie Vision camera. We planted these cameras at different intersections along our study segment to capture traffic volumes at those intersections. And then at the same time, we collected general traffic travel time along the corridor. And then we also collected transit data, the speed profile. We used GPS to collect speed profile along the corridor, bus travel time, and then at the same time we collected boarding and alighting counts, at different bus stops along the study corridor, ridership and schedule adherence. And then we got signal timing and phasing plans from the Department of Public Works, Nashville, Tennessee. So after we collected our data, we went further to develop our model in Vism. So we coded the corridor geometry just the way you see the way you see the corridor in real life. So we followed the corridor geometry. As we can see from the picture, this is just a capture of what some of our intersections look like. So we actually followed the geometry uh, of the corridor. And then we use connectors to model turning movements. Like if you're going left or going right, we use connectors in Vism to model that. And then we use the Weirdman 74 car following model to model the aggressive behavior of drivers in the modern urban motorized environment, because drivers could be sometimes very aggressive. So we use the Weirdman 74 car following model. And then we coded our vehicle composition and the desired speed distribution from sites that we got from sites. And then we coded bus dwell time, boarding and alighting count, passenger flow characteristics, bus departure time offsets, and the bus of occupancy as part of bus stop properties and public transportation line properties. Then we also coded our turning movement counts. Remember, I said we generated estimated origin destination matrix. Okay, so after generating that, we coded that into Vism via dynamic assignment. It, why we chose to use dynamic assignment is because when you have a large network, it's usually very cumbersome and could lead to a lot of errors when you're trying to enter the routes manually. So to avoid those errors, we chose to use dynamic assignment. So this picture actually shows a portion of this, the part of Vism where we coded our origin destination matrix. You see the picture on the left. That's the origin destination matrix for different zones. And then we coded the parameters. It's a lot of process, but just to make it brief, we coded the vehicle composition and classes based on the origin destination matrix in Vism. So we went further to calibrate our model after we had finished developing our model. We calibrated the origin destination matrix. So when you code the matrix in Vism, Vism gives you an output after several simulation runs. So we compare the output from Vism to what we coded to see if they actually match, if what we coded into Vism is what Vism is giving us. That's part of model volume calibration or OD matrix calibration. And then we adjusted parameters so that the speed we put in Vism, um, the percentage error between the speed we put in Vism and the speed we observed on site is less than 5%. And then we validated the. Okay, before I continue, calibration is the process of making sure that your model replicates what's on site. So if drivers are driving 50 miles per hour on site or 40 miles per hour on the field, they should be driving something close to that in your model. It should be plus or minus 5. It shouldn't be. It should just be something close to what's happening on site. And then we went further to validate our model using a parameter which was not used in the development process, and that parameter was travel time. And then we compared the time it would take a vehicle to travel from the beginning of the link to the end of the link. We compared the result from Vism and what we got from site, and our result was less than 15%. Specifically, it was 14.4%. Okay, so So when we were sure that our model replicates real life condition or replicates the existing condition, we that was when we added the transit signal priority logic. Okay, so there are two major ways to control transit signal priority: the passive priority and the active priority strategy. The passive priority strategy allocates green time to approaches having higher bus flow than others. So it just gives green time to a specific approach that has more bus flow compared to others. But the active priority actually adjusts the signal timing to respond to a bus that is detected at a certain distance to the intersection. So we actually adopted the active priority strategy because the passive priority strategy could be wasting a lot of green time. So we only give green time when there is a bus approaching the intersection. So that's the approach we adopted for our study. And then we use both the green extension and the red truncation priority strategy. As we can see from the picture, we'll start with the green extension strategy. You see, we have a normal cycle from red to green, and then from green to amber to red, and then it goes like that. But if you look at the priority cycle for the green extension, you see that when a bus as the bus arrives at the intersection, there's an extension of green. If you compare the normal cycle to the priority cycle, you see that there's an extension of green, and the green eats into the red time. So that is what is called green extension. So it's like taking some part of the red time and converting it to a green time because we are detecting a bus, say a certain distance away from the intersection. And then for the red truncation, if you look at the normal cycle and the priority cycle, you can see that there is an early return of green. There is the red phase is shortened for the priority cycle. The red phase is shortened to return an early green for the bus that is detected at the intersection. And how were we able to achieve this? We developed a code using the vehicle actuated programming language. Okay, so this is our logic. This is the logic behind our code. This is what we use. So this is just a snapshot of our model and the detectors that actually control the logic. We see there's a bus detector located 75 meters away from the traffic, the stop line, and then we have our minimum recall detectors and our gap out detectors. The minimum recall detectors make sure that each phases have at least used up their minimum green time before at least each phase is used up their minimum green time, whether there is a demand on that phase or not. And then our gap out detectors take care of terminates a phase if there is no vehicle call on that phase. So how does our logic, the logic we created in vehicle actuated programming language, this is how it works. Now the question is a bus detected? If the answer is no, the signal controller continues its normal operation. But if the answer is yes, the question is the green time enough for the bus to go through the intersection? If the answer is yes, the green time is enough, then there is no need for priority. The signal controller continues its normal operation. But if the answer is no, if the green time is not enough to allow the bus to go through the intersection, the signal controller calculates the green extension time that will be able to allow the bus go through the intersection, and then it executes this green extension time. Now, is the bus stopped by a red signal? If the answer is no, that means the signal is green. Then he goes through the green extension process. If the answer is yes, the question is, have other conflicting phases, other phases which conflict with the bus priority approach, have they been able to at least use up their minimum green time? If the answer is no, the bus will have to wait until at least other conflicting phases have used up their minimum green time before the signal controller calculates the priority green time for the bus. So basically, this is the principle behind the code we developed using a vehicle actuated programming language. So our results. So this is our validation and calibration results for the origin destination matrix. So we can see that when we compared field volumes to what we estimated, it gave us an R square of 0.8569. That's showing that there is it closely match our field data matches our estimated origin destination matrix, and then we calibrated the output from our VISM. We compared the output from our VISM to what we estimated, and we find out it gave an R square value of 0.9984. This is actually telling us that they match, they are closely related. Okay, so after our evaluation, these are our travel time results. So these results are the results along the priority approach. We call it the mainline approach. That's the bus corridor. So as we can see from the results, buses, it will take a bus a longer time to travel from the beginning of the link to the end of the link compared to other vehicle classes. Okay, so and from the results, we can see that there's a reduction in travel time for buses after we have added TSP. The blue bars are base condition, that there is no TSP, and the red bars are after condition, that's after TSP. So there's a reduction in bus travel time after we added TSP. And we can also see from the results that TSP will not just favor only buses alone, but will favor other vehicle classes which are utilizing the priority approach. The same thing goes to our vehicle delay. We evaluate the amount of delay reduction, and we also discovered that there is a reduction in delay for buses and other vehicles using the priority approach after implementation of TSP. Then we went further to see how much TSP will favor schedule adherence. You know, most times buses are late, and we that's what makes transit less attractive because of this lateness. So we went further to evaluate to see how much lateness we can recover. How can we improve on schedule adherence? So from our results, we can see that there's a high increase in late bus recovery. We will see the summary of the results as we continue. So we went further to evaluate the impact TSP will have on side streets, like the crossing street. Will it have a significant effect on other road users, on the conflicting approaches? And yes, we discovered that TSP will increase delay for the side street users. There will be a slight increase in delay, though not excessive, but of course there will be an increase in delay because we are taking some of their green time and giving to the priority approach. So as you can see from these results, there is an increase in delay for vehicles on the side street. Okay, we also evaluated the impact TSP will have on the overall performance of the corridor in terms of level of service. And as we can see from this result, that level of service did not really change. Level of service did not really change except for one intersection, and that's as a result of high traffic volume. So in conclusion, TSP will recover bus lateness by 34.16%. TSP will reduce bus travel time by 5% to 10%. Will reduce bus travel time for other vehicles by 5.8%, reduce delay by 11% to 23%, and TSP will increase side street delay by 15.9%. Based on our research, TSP will greatly influence community livability, improve bus travel time, reduce bus delay at traffic signal, recover bus lateness at bus stops. and of course make our public transportation very attractive. Thank you.